By numerical examples, I mean things where you have numbers. You actually have some numbers, you actually have some computation, some thought, some analysis, some modeling, whatever. You got to do it. If there's no numbers, it's not math, okay? It's literature, okay? So we don't do literature here, we do math here. And the fourth thing is homework. You got to do it yourself. You can do all these three things, but unless you try it yourself, you don't realize how little you understood. Okay, so when I was writing the textbook, I was learning stuff I hadn't learned before. So I said, yeah, I get it. And then I'd start writing a numerical example, you know, as part of the text. And halfway through, I said, I don't know what I'm doing here. I'm just completely lost. And only by doing did I learn what it was. Okay, so you have to learn by doing. And that's why you have all these homework examples, and that's here the midterm, the final, because this will teach you what you need. Okay, so those are the four things you need to have, and that's why I have it over there. Okay. Any questions about that? Okay, so in going with grading, there's an equivalent concept now. Can you see this here? Yeah, you can see that. Okay, this is called the karma of grading. So karma is this very deep concept, which means, you know, you can't escape the consequences of your actions. In this case, what I'm talking about is sometimes you'll get a grade which you think you didn't deserve. So you really understood everything, but in the final you kind of messed up and you got a really bad mark which you really shouldn't have. But you know the material, no problem. No problem. Because of karma of grading, when you need that material, you will have it at your fingertips. It's not a final, it's a real world. You need, you know, to control theory, you need to build a PID controller, you'll know what it is. And so even though you got a bad grade, you'll still do well. Anyway, the grade doesn't matter. Okay. On the other hand, you got lucky, you know, all the questions were turned out to be exactly the ones that you asked, and that you prepared for, and you got a good grade even though you didn't deserve it, no problem. When you actually need to know the stuff, you won't have it. Okay. And you will fail miserably. So I don't need to solve the problem for you. Life will take care of it. That's the karma of grading. Okay. So, so don't worry too much about grading as well. Oh, I forgot to mention about the midterms and the finals. One more thing, which is the question. So for the questions for the midterm and the final, I'll be setting them, but here's something that I learned from a colleague of mine, which I'm going to try out. You can suggest questions for the midterm and final. Okay, you can say, I suggest the following question, and you should give me the answer as well, so I can make sure you know the answer. If I select your question and answer and put it in the final, you get an edge because you know the answer already, right? So it's in your best interest to send me good questions and good answers. Of course, it's good for me too. But we both win. So you win because you get a better mark, which doesn't really matter, but you get a better mark anyway. And I win because I get these questions. And if they're really good, I'll put them in the book and I'll credit you and say, this question was suggested by, you know, so and so. I know your name by then, I suppose. And so your name will appear in print, and you know that's hopefully it's a nice thing. When you write your CV, you can say my question was selected for inclusion in a graduate textbook, you know, and maybe somebody will give you a job because of that. Who knows? So feel free to suggest questions, you know, relevant to the course. You don't need to put it on Piazza. You can just email it to me, and that's good. Okay, I think I've covered almost anything. Any questions? And then I have a last few things, and then we can almost start the materials. Any other questions? Yes?
You keep mentioning the textbook, so you are writing a textbook.
I've written, yeah.
Not here. We have a textbook.
What does it mean, do you have a textbook?
I mean, is there an assigned textbook for this?
Yeah, the assigned textbook is Mathematical Frontier Computer Networking. Well, I'm going to, there's a PDF for the chapter in linear algebra. It's on Piazza. If you go to Piazza, you can click on it and you'll get the PDF for linear algebra, and you'll get the PDFs for the other chapters as well. Okay. Oh yeah, which I should remind you, let me actually go through that since you asked. There are 4 PDFs, one for each chapter. If I do probability, it'll be a chapter, probability chapter. There are already PDFs online on my website, which are the PDFs for the first draft of the book, which I finished some months ago. Okay, so if you go there, you'll see all 9 chapters are online. You can download them for free. Okay. For this class, I'm using the second draft. The second draft has fixed a lot of problems. It's easier to understand. The English is cleaned up and so on. The second draft is not public. Okay, so the second draft is so the publisher will not let me put the second draft publicly. Okay, because I did it using their resources, their editing resources and so on. So, but I'm going to use it for this course. So the PDFs are there. Feel free to use it. Please don't redistribute it to outside people because, and I'm not supposed to do that. Just keep it to yourself. Those 4 PDFs. But the first draft PDFs, all of them are online. Yeah. Okay. Yeah. The other thing about the course textbook is that read everything carefully. Each sentence is there because of a reason. If the sentence is not needed, I took it out. Okay. If there are any words that are not needed, I took those out too. So don't skip anything. Read through it carefully. It is a textbook, and I spent about 4 years writing it. So I think it's reasonably good. Okay. Yeah. Any other questions? Okay. Okay. So some more rules for the class. I tend to be fairly strict in terms of classroom things. So please don't have conversations with your friends or talking. I don't like that. Try to avoid sending text messages to each other or to your friends or whatever. Using your cell phones or talking on your cell phones. If you want to use your laptop to look at the material, you can do that, though I suggest it might be easier for you to just print it out and mark it up or write on it. Having a laptop in front of you, even if you're looking at the text, is pretty distracting. So as I see this person in the corner who is completely engaged in something, I don't know what, but not listening to me actually. So this is where chalk is pretty useful. But that person in the corner actually doesn't even know I'm talking about him. He's completely immersed in some out-of-the-body experience. So let's all look at him. Hi. How are you doing? Are you happy to be in this class?
Yes.
Oh, good. I'm glad to hear that. Because
I know you because I can't keep up.
I see, but I was talking about you for the last 30 seconds. And I was saying, you in the corner, you're not paying attention. And I'm talking about you, and so on, and you didn't actually listen to a word that I said.
Sorry, sometimes
you get distracted. So you're a perfect example of why I prefer not to have laptops in the classroom and to use a printed copy of the notes. Everything that I'll be teaching will be in the textbook, in that printed stuff, and there's absolutely no reason for you to not just write on it. So generally speaking, unless you really need to have a laptop, I would recommend not bringing it to you. Bring it because if I feel that you're not actually paying attention, I will do exactly what I did to him, and you may not like it. Okay, let's see. So yeah, and it starts on time, as I mentioned over here. Those are the sort of the rules. Okay, any other questions about sort of the rules? Okay. Generally speaking, the goal of the rules is to make sure that the people around you aren't getting distracted, because math is hard, right? It's not an easy subject. You have to be focused. And if somebody next to you is munching away on on chips, crunch, 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 and it's really kind of distracting, or somebody is I don't know what, playing a video game or watching YouTube or something. It's very distracting. Distracting for me as instructor, and it's distracting for the students, so I don't like that. The other thing, by the way, I'm going to explain to you something really remarkable property in physics, which is that if you can see me, I can see you. It's actually true. But most people feel that if you're sitting in class, they can see the instructor, but it's a one-way mirror, and they can do what they want, and the person sitting there is blind, not true. It's you can try it for yourself. Stand over here, ask your friend if you can see me, can you see them or not? And almost always you'll find it's a bilaterally symmetric relationship. It's not a one-one relationship. It's a bidirectional relationship. So if you're sitting there, I can see you. If you can see me, I can see you. If I'm sitting here, hiding over here, I can't see you and you can't see me. Okay, but it's a symmetric relationship. So don't think I can't see you. Okay. Now I've said this, and about 3 weeks from now, somebody's going to do something really stupid. I don't know which one of you it is. Thinking I can't see it. But I can. Okay, on that nice note, let me, I'm going to do one example, then we'll do a break, and then we'll actually start with this whole topic. Okay, so I just want to quickly check. So let's see. How many of you are from computer science? Okay, or maybe we should turn it around. How many people are not in computer science? Okay, 1, 2, 3, 4, 5. Okay, and how many PhD students? Okay, about half. Okay, and I already asked. So first year students is how many of your first year? Okay, so about okay, all right, it's good. Just want to get a sense. Okay, so I'm going to start with a very simple example. Okay, so what is this? Okay, anybody who wants to answer? It's not a complicated question, huh? Who said that? Triangle. It's a triangle. Why is it a triangle? It has three? It's a 3 vertices. Is that a vertex over there, or it kind of looks kind of messy over there? It's a messed up triangle. Does a triangle have straight lines? Yeah. Is that a straight line? No. So why? It's not a triangle. Approximately a triangle.
It has a concept of triangle.
You really want to be the person? Okay, good. Okay, it's a concept of triangle. Okay, so this is not a straight line, and that's not a straight line. That's not even a vertex. But you said it's a triangle. So you're not right. It's not a triangle. So what is it?
You tried to write a triangle, and we understood that you want to write a triangle.
So I drew something which is clearly not a triangle. It's like it's not no straight lines, not even vertices, and you tell me it's a triangle. So you're lying to me.
In your homepage, there's a picture.
Yeah.
It's not you.
Yeah.
But
Okay, don't change the topic here. So the thing is, can you ever have a real triangle? Does such a thing exist? Can I actually draw a triangle?
no.
No. Why not?
The definition is super hard.
Yeah.
You can't achieve unlimited degrees.
Right. In real life. So when I draw a line, no matter how straight I try to draw it, even if I use a laser and this and that, I'm going to have, essentially atomic something, right? It's going to be some atoms, and the atoms are wiggly and move around and so on. So I'm never going to have a straight line. So if I can't have a straight line, I can't have a triangle. Yet everybody said that's a triangle. So how is it that you know what a triangle is, though you've never seen one? You cannot possibly have seen a triangle in your whole life. You've never seen a straight line in your whole life either, right? So somehow you know what a triangle is without having ever seen one. It's like saying there is this animal, which has all those funny kind of colors and this and that. You've never seen it in your whole life. You've never even seen a picture of it that's even closely resembling it, because you see there are no straight lines and yet you recognize it. So what happened? How did that happen? Imagination. So how did the imagination? What happened in the imagination? At what point did you say, yeah, that's a straight line or that's a triangle?
Maybe it's because of the abstraction.
The abstraction. So the abstraction comes from the brain and from examples, right? So I say this is a triangle and that's a triangle, that's a triangle. I kind of draw all these things that are not triangles. Okay? I find all these things that are not triangles and I say, what's common to them? And in the triangle, it's actually in your brain. It's not on the board. In fact, all triangles are in your brain. They don't exist. Ideal triangles do not exist. They only exist in your brain, or our brains, I should say. They're conceptual things. So this insight is not mine. This insight actually is due to Socrates. This example of drawing a triangle, it was drawn in some sand, is from Plato in, I believe, the 5th book of the Republic, or I don't know which book of the Republic. I think it's the 5th. There's a nobleman who comes by and Socrates draws this triangle and says, "What is this?" And the nobleman says, "It's a triangle." And then the exact same dialogue that happened right now happened then, 600 BC. And it was so important that Plato actually wrote it all down. So don't feel bad, because people have been making these mistakes for 3,000 years. When somebody asks you this, just keep quiet. Don't say it's a triangle. What you should be saying is, you're trying to approximate the concept of a triangle using real world straight lines, which are not really straight lines, but through my intense understanding of philosophy, I realize that you are trying to communicate this concept. If you do that, that would be good. But there's an important point. The important point that Plato made out of this dialogue, that Socrates actually is supposed to have made from this dialogue, was that he said, first, triangles only exist in your brain. They don't actually exist in real life. And second, we already know everything that we wish to know. We just have to realize that we know it. Okay? I mean, that was the point that Plato was making. We kind of already know these things. So I disagree with that. I don't think that's true. Actually, what I think is true is this. When you see sufficiently many examples of a concept, you abstract from it. Okay? But the abstraction process must happen on your side. Okay? I can't do the abstraction. I can show you concept 1, concept 2, whatever. I can show the triangle, but your brain has to put the triangle inside it. Your brain has to do the effort to change the connections between the neurons in such a way that the concept of triangle exists inside it. Okay? In the same way, I can explain to you eigenvalue over and over again, but the concept of eigenvalue is in your brain. It's not a real thing. It's in your brain. Okay? You have to work. You have to do those 4 things. You have to have the intuition, you have to read the math notation, you have to look at the numerical examples and to do the homework. Only then will the concept go inside your brain. So as an instructor, as any instructor for anything, all we can do is show you examples, show you these things over here. But until you work at it, it's not going to go inside your brain. Okay? Education, at the end of the day, is essentially reprogramming your brain. Okay? What you want to do at the end of this class is to have your brain that looks different from the class than before you got in, right? This is what you can think of as practical neuroprogramming. Okay, I'm changing the structure of your brain by talking at you and drawing stuff on a board. Okay, it's unbelievable, but it works. Right? At the end of this course, hopefully, by just talking to you and drawing stuff with chalk on a blackboard, your brain has got changed in some nice way. Okay. And it will only happen if you work at it, if you are actually participating in it and you're thinking about it, and your thoughts and your understanding will actually change the structure of your brain. Okay? So that's the way it works. Now how this happens, nobody really knows. I don't know. I just draw all these triangles and then suddenly you say, yeah, I know what a triangle is. Okay? And I'm going to try doing that for PID controllers and mutual information and these other concepts as well. But at the end of the day, it has to come from inside you. Okay? Any questions about that? Okay, good. So let's embark upon our brain programming or brain modification. And I'm going to start with the section linear algebra. But I noticed that I've been talking to you for about an hour. It's time for a little break. So I'm going to tell you my first story, and then we'll do linear algebra. So the first story is the difference between knowledge and wisdom. Okay. So my grandfather passed away some years ago, and he used to tell me all these stories. And each story would taught me something. So this story, I think, is from my grandfather. I'm not really sure, but I think it is. I've read many other stories. So there were these four young men who were living in this village who were all very good at various things. They'd studied very hard and they're really very good at stuff. And they had a friend who was not very good at all. He was kind of a dumb guy. Okay, but they grew up together, so they decided they would just keep him. stay friends with him even though he was a dumb guy. He's really sleepy. You want a cup of coffee or something? Okay. So what happened is that when they graduated from their school, they wanted to go to a big city, and they decided that they would all go together. So the 4 guys said, yeah, we're going to go to this great university, go to a big city. But this dumb guy said, I want to come along too. Said, okay, fine, we've known each other all our lives, we can go along. So this is in the old days, these are forests all over the place. And this was in India, so they had tigers even. And so they're walking through this path, and they see these bones lying there. And the first smart guy says, I know what those bones are tiger bones. The second smart guy says, I'm so smart I can assemble all of them and make a complete skeleton out of these tigers. So sure enough, gets together, puts all the stuff together, a tiger skeleton, it's all set up. The third smart guy says, I actually learned a bunch of magic and I can put all the flesh and bones and skin on this just by uttering these magic syllables. So he did that, and tiger was, magically put into this thing. And the fourth guy says, I am smarter than all of you. You guys think you're smart. I'm really smart. I'm going to bring it to life. The dumb guy says, okay, you guys are so smart. Let me climb a tree first. Okay. And then you can just, no, you guys, you don't know what you're doing. And so the dumb guy says, okay, he just goes and climbs a tree. And the fourth guy, brings the tiger to life. And of course, the tiger is hungry. It hasn't had anything to eat who knows how many years. It eats all the smart people, and the dumb guy is sitting on top. And the question is, who was smart? And who's dumb? So that's it. That's the story. So don't confuse knowledge and wisdom. And this story is from a collection of stories called the Panchatantra, and there'll be many more stories from the Panchatantra eventually. But that was just the story to start with. Okay. So let's start with linear algebra. So this course is the only fun lecture in the whole class. After this, it gets pretty boring, and there's no more fun stuff. That's all you get. Okay. So let's start with linear algebra. Today, I'm just going to cover the basic idea of a vector and a matrix, and some elementary operations on vectors and matrices. So let me start with the concept of a vector. Okay, so all of you have seen what a vector is probably, and kind of have used it, but I'm trying to explain to you intuitively what a vector is. So a vector is just an ordered list, okay? And it arises because we tend to use ordered lists a lot, okay? We're doing some stuff, when you're doing some research, we end up using ordered lists a lot. So let me give an example of this. Let's say that, so my examples will all come from computer networking, because of the computer networking, but I don't really expect you to understand or I don't expect you to have taken a course in computer networking, but let's just use this. So let's say here's a campus network, and then there's an access link, and that goes to some ISP, and on this access link, I'm going to put a monitor, and then I'm looking at the number of UDP packets and TCP packets, okay? Okay, and so on the first, let's say in the first interval, which could be the first second, I had 20 UDP packets and 30 TCP packets, and then I have 40 packets and 20 packets, something like that. I can think of an ordered list that looks like this. I can say 20, 40, where implicitly we mean 20 UDP and 40 TCP. Sorry, what am I doing? 30. Okay, so these two things over here. And so this is a vector of number of TCP and UDP packets. And so if I draw another vector like this, I can say 40, 20. Again, that's a vector. So we can take essentially any set of experiments, okay, and represent the results from those in terms of a vector. So that's where vectors come from. Vectors come from the necessity of representing things that are related to each other in an ordered fashion. Okay? Question? No? Okay. So that's the basis for a vector. So wherever you have ordered lists, we can think of using a vector to represent it. Okay. So each thing over here is called an element. That's the term that we use. And the number of elements in the vector is called its dimension. Okay, so that's a two-dimensional vector. And the reason why we use dimension is because we can think of the following space or following graph. Over here I have the number of UDP packets, they have number of TCP packets. And then I can draw a point on it 20, 30. So let's say this is 10. So 20, 30 is this point over here. So there is a very clear kind of, 20, 30 or 40, 20. So that would be 40, 20. So these two vectors are clearly just points in this two-dimensional graph. Okay, so we can think of a one-to-one mapping between these two vectors and these 2 points. Okay, so points in two-dimensional space correspond one-to-one with vectors with 2 elements. Okay, over here we call that the dimension of that space. Okay, any questions about this? Okay, so now let's make it a little bit more interesting. So I said it's TCP and UDP, but I could also have, let's say, number of ICMP packets. So let's say I have 30 ICMP packets and I have 10 ICMP packets. So now these vectors would correspond to points in three-dimensional space. So I have an ICMP axis, and then I would have points in three-dimensional space. Okay, but I could go further. Let's say I'm measuring 8 protocols. Okay, I'm measuring 8 protocols. So let's just draw the protocol like the values as x1, x2, all the way up to x8. Okay, how many dimension space do I have? It's 8-dimensional space, right? But that isn't really a problem. We can't imagine it. We can't draw it, right? For us, the dimensionality of the vector doesn't really cause need to cause confusion about what is the space, right? Because from our perspective, it's 8 dimensions. We just operate on it using 8 numbers, and it's 8 dimensions. It's a point in 8-dimensional space. So when somebody comes in and says, "Oh, I'm working in 13-dimensional space," it's like, "Oh, no big deal. It's only a vector with 13 numbers." So all the physicists talk about 13 dimensions in space, right? You hear about string theory with 13 dimensions of space. It's not a big deal. It's just a vector with 13 numbers. You don't need to worry about it. Okay. In fact, you can't, because you can't imagine. I can imagine 4 dimensions. Beyond 4 dimensions, nobody really knows what it means. But we're perfectly happy writing vectors with 8, 10. And actually, we can do something even funnier, which is we can go infinite dimension. Okay. There is something where, what does this correspond to? It corresponds to an ordered set which has no end. Okay, which has no end. We know. So let's say I have a monitoring device over here on my campus network, and I started the monitoring device, last week, and I'm going to keep measuring every nanosecond forever. Okay, I'm never going to take it off. I'm just going to keep measuring every nanosecond. So I can see I have a very, very, very long list. And my friend also started off at the same time on another link. So we have 2 vectors, and both are infinite dimensional. Okay, which just means we don't know how many dimensions. So again, infinite dimensional, though it sounds very complicated, it just means I have a list which is very long. It's essentially infinitely long. Okay, so that's how we deal with infinite dimensions. So when somebody says I'm dealing with 4 dimensions, 5 dimensions, 13 dimensions, or infinite dimensions, it sounds very complicated. It just means that this list is very long. Okay, so each point in an infinite dimensional space corresponds just to a list of numbers which has no limit. Okay. Any questions about that? Yeah.
If there is an infinite dimension vector, how is it an ordered list?
Which means the ordered list, meaning that we can identify, like, this is the first time instant, the second time instant, third time instant, for example. It's ordered, right? So I know, like, the 5 millionth element corresponds to the 5 millionth observation. So there's an order. I can't change the order. Just the dimensionality is infinite. That's all. Okay. So obviously, I can have the following vector, which is 0, 0, whatever, and that's called the 0 vector. and that corresponds obviously to the origin of the space. Okay. Any questions about that? So that's a standard zero vector. Now vectors can be written in two forms. You can write it like this. This is called a row vector, and then we can write vectors like this: x1, x2, xn. This is a column vector. It's a column vector or a row vector. So those are the two kinds of vectors that we have over here. Okay. So that's all you need to know about vectors so far. Any questions about that so far? Okay. Most textbooks will talk about vectors and dimensions, but they don't really go into infinite dimensions, which actually turns out to be pretty straightforward. Okay, so what happens if I do the following? I have a vector, and I have another two row vectors, and I just put this like that. Okay, here is what I get, what I call as a matrix. So here I have x1, x2, xn. And I'll just put 1. That means that these are the first elements, and then x21, x22, x2n. And let me get rid of these extra stuff over here. And this is a matrix. Okay, this is a matrix which has two rows, and it has over here n columns. So we'll call it a 2 into n matrix. Okay, 2 by n matrix. So we first say the rows, the number of columns, that's a matrix. Now, the interesting thing about a vector is that these things are basically unrelated. So ordered list, it could be anything, TCP count, UDP count, whatever. There's no relationship between the two. But in a matrix, all these guys are the first elements of vectors. So they're all the same thing. They're all, in this case, could be TCP counts or UDP counts or whatever it is. They're also the columns in a matrix have significance because they're all the same thing. Okay. Of course, there's nothing that stops you from creating a matrix with completely random stuff, but that's not really helpful. Okay. For almost everything that we do, we will have the fact that these vectors, these row vectors, are going to have the same order. Okay. And again, matrices can be infinite dimensional. So in this case, we actually have two dimensions. This is the first dimension and the second dimension of the matrix. Okay. Any questions about this? Is just kind of presentation? Yeah.
Why do you choose column? I don't see any difference between column and row.
Why do you choose those? There's no particular. It's just what's convenient. There's no reason one is preferred over the other. When we talk about multiplication, it will become clear why we need them. But for right now, there's no reason. You can choose one or the other. Yeah. There's no difference. Any other questions? Okay, so that's the basic stuff. So now let's look at the little bit more into these matrices and where they're coming from. And I think I have 5 minutes, so I'm going to talk about just. Oops, whoa. Okay. All right. So let's focus on these elements over here. As I show, I write elements are typically written like this. Let's say A. And then there'll be the row number and then the column number. Okay, so it'll be A12 and then you have A21. So if I have matrix, this is A11, A12. So that's row 1, column 2. That's A12 and this is A21, for example. So don't confuse the two. Okay, A21 and A12 are not the same thing. Okay. Typically, in almost everything that we do, the A sub I, Aij, which is the ijth element, will form a field. And that's important. Okay, so I'll explain what a field is in just a moment. But in almost all the work that, now you can put anything in matrices. You can put strings, you can put whatever you want. But almost all the work we'll do, it's convenient for that Aij's form a field. And so we'll call it a matrix over a field. Okay, so what's a field? Okay. So, so I'm sure you've seen the word field before. So I'm going to explain what a field is. So a field is basically something which there's a set and there's an there are operations on the set. And the operations are given the word are given the symbols plus and star, which correspond. Mentally, you can think of a field as being the integers. Okay, positive and negative integers form a field over the well-known standard operations of addition and multiplication. But in set theory, we can generalize this where the operations will be just given the term plus and star, and then we can do it over any set, which could be finite or infinite. So in case of the integers, it's infinite field, but we can think about finite field. Okay, and so in our work, again, we'll be doing this over the reals. Okay, generally speaking, we'll be matrices on the reals, which form a field. So how do you form a field? You need to define 6 things. So you need to have one closure. Okay, closure means that if A and B are 2 elements belong to a field F, okay, and then A plus B, okay, basically A plus B belongs to F, and A star B, whoops, belongs to F as well. So we write this funny looking F as the name of the field, so it could be the reals or the integers or whatever. Okay, so closure just means that any operation I do on the elements of the field is going to result in some other element of the field. So it's closed. We don't have to go outside the field. You can stay in the same field. So if you multiply 2 reals, you get a real. If you add 2 reals, you get a real. So that's there. The second one is commutativity, which means the order doesn't matter. So A plus B equals B plus A star B equals B star A. So we don't know what the operations plus and star necessarily mean, but commutativity is going to hold. And then the third thing is associativity. And that means that basically A plus B plus C equals A plus. So order doesn't matter, and the same thing is true. This is associativity of addition. And then a similar thing can be described for associativity of multiplication, which means A star B star C is the same as, it doesn't matter which order you do it. Then 4, we have the identity. So there exists some element called 1 such that A star 1 equals A. That's the multiplicative identity. And there exists an element called 0 such that A plus 0 equals A. So again, we normally think of this as the 0 and 1 in the integers or the reals, but in a general field, it could be anything. And then we have the inverse. And the inverse basically says that there is something which is going to, so that if for all A that belong to the field F, there exists a B such that A star B equals 1. So the 1 over B, so in this case, the integers will not form a field, because we won't have the multiplicative inverse. So reals form a field, or the rationals form a field. So this is why integers will not form a field. So we're now kind of getting more specialized. Say, okay, field has this multiplicative inverse, so we can't do that with the integers. And then we need for all A belong to F, there exists a B for the additive inverse such that A plus B equals 0. That's a 0 element, so that's a negative if you want. And then finally we have this thing called distributivity. I'm running out of space here, I think. So I'll just do it over here. Distributivity, and basically what that says is that A star B plus C equals A star B plus A star C. Okay, so that's the distributive operation. And with these 6 sort of axioms, we essentially can define a field. So integers don't form a field, rationals form a field, and so on, and complex numbers form a field. We'll usually do our work in the reals. Okay, we'll assume that, yeah.
So multiplicative inverse does not exist for
It not exist for 0. Yes, you're right. Let me see. How do we get rid of that? I have to think about that. So we need to add some. Yeah, there's an exception except for the 0 element, I guess. So except for. So we need to, yeah. Clearly I forgot to add that little thing. So whenever you do something in math, there's always a little dot at the end you need to worry about, in which case, which I forgot over here. So we won't be focusing as much on fields. All we'll need the field properties for is to prove properties of matrices which are on the fields, because when you add two matrices and so on, this is what's going to show up. Okay, I'm out of time, so I'm going to stop here. For the next lecture, so I just covered basically the first page in the chapter. We'll do algebra and then dimensions and stuff like that. So independence. Okay, so next lecture, please try and bring the homework problem set 1 on Piazza. Bring it in, and hand it in. Actually, hand it in to a neighbor to have it graded. Okay.